Hello everyone! In this video we will continue to examine topic 12, quantum and nuclear physics. Topic 12.1, the interaction of matter with radiation and in particular the photoelectric effect. Alright, so finally we are prepared using what we know about the photon model to explain the 4 experimental results discussed before from the photoelectric effect. And we're going to do so by reference to this single explanation. In the photoelectric effect, each photon of energy E equals hf is absorbed by a single electron, and that electron is ejected with the energy of that photon minus the energy required to eject the electron from the metal itself. So, if we're taking a look at these results, sorry, I'm going to start with number 1 here. We're going to consider each of the things that have happened and what would happen on the wave model versus what will happen on the photon model. So our explanation of it on the photon model is here, and then what we would expect to happen on the wave model is right here. You should be comfortable explaining both. So on the wave model, we would expect that as the intensity increases, so should the maximum kinetic energy in the stopping voltage, right? That's because as you crank up the intensity of a wave, you're cranking up the energy delivered by that wave, and so the energy absorbed by the electrons in the metal should grow. But what happens is as the intensity increases, the energy of each particular photon stays constant because it's related to the frequency. And so does, therefore, the maximum kinetic energy of the ejected photoelectrons. All right? So if the energy of each photon is staying constant and it's absorbed by an electron, then that electron is going to have, at maximum, a certain amount of kinetic energy, and that's it. That's all. Okay? That is the only amount of energy it's going to have because the energy of each photon stays constant. What happens, though, as the intensity increases is that the number of photons emitted from the source increases, and therefore you get more electrons emitted. And as a result, the maximum photocurrent increases. So even though the stopping voltage doesn't increase, the photocurrent, the maximum photocurrent, does. What about our second observation? Well, according to the wave theory, the stopping voltage and the maximum kinetic energy of those electrons should depend on the intensity, but not the frequency. The frequency of a wave doesn't affect its amplitude. Okay, so straight up, that's just not how the amplitude of a typical wave works. It's not dependent on the frequency, and therefore the energy of that wave isn't normally dependent on the frequency of the wave. On the photon theory, however, as each photon is absorbed by a single electron, and the energy of that photon is related to its frequency, then the maximum kinetic energy of the photoelectron will be directly related to the frequency of the light. If you increase the frequency of the light, you go from optical to UV, you are giving each photon that you send more energy. The photons come with higher energy per packet, and they're absorbed by a single electron, which means that your maximum kinetic energy of those ejected photoelectrons, and therefore your stopping voltage, is going to directly depend on the frequency of the light coming in. That is directly tied, number 2 is directly tied to this proposal right here, that E gamma is equal to HF. All right, what about our third result? Well, on the wave theory, as the intensity increases, so should the maximum kinetic energy and stopping voltage, no matter the frequency, for the reasons we discussed in number 2. But on the photon theory, if the energy of the incoming photons is insufficient to eject the electron in the first place, then no electrons will be ejected regardless of the intensity or the number of photons sent. So you crank up the intensity and the number of photons. If each of those photons doesn't have enough energy to eject an electron, right? If a single photon doesn't have enough energy to eject an electron, then none of them will be ejected, even if you crank the intensity up as high as you can. You're just sending more and more low energy photons at the metal, and it's not enough to eject an electron. So At this point, we can stop to define a useful value, which is known as the work function, which is a terrible name, but we're stuck with it. The work function is the minimum energy required to eject an electron from a metal, from a photosurface. It is given the symbol phi, and it is analogous to the first ionization energy on a bare atom. Okay, it's the same idea, except instead of a bare atom, you're talking about a metal. So how much energy is required from a single incoming photon to eject the electron from the metal? That's known as the work function, and it depends on the metal. Notice that the work function is therefore equal to h times the threshold frequency, that limiting frequency below which you get no photoelectrons at all. So that's the work function. And then finally, all right, on our wave theory, at low intensities, there should be a noticeable time delay as energy builds up to eject the electrons. So on our wave theory, if we've got a very low intensity UV light, we should actually have to wait for a little while for the energy being absorbed by the metal to build up until you can eject an electron. But what happens on the photon theory is that as long as the frequency is larger than the threshold frequency, an electron will be ejected with 0 time delay. That means we detect a photocurrent as soon as that electron reaches that cathode, the moment a single photon ejects that electron and the electron reaches the electrode. That's it. So there's no time delay. You don't have to wait for energy to build up. An electron is ejected immediately as long as the frequency is larger than the threshold frequency.